Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I will help get you started with Class 10, Simple Linear Regression. So here we are at the website. We'll go down to the timetable and scroll down to class number 10. So number 10 does not have an RMD or HTML file over here. That means it must be in the outline that we started in class 5. So I'm going over to RStudio, where I've already opened the file that I was working on last time. And because this is a new work session, I'm going to save this as the date, and since it's the same day, I'm going to append it with the letter A. All right, let's knit this to make sure we're starting with a file that is working just fine. And then we'll scroll down to class 10 to read the rubric and get started. While this is compiling, let's go back to the website, scroll back up to where you will use these files as a model for your assignment. I'm going to be looking at this HTML file, but you're welcome to either look at the one from last year, which is here, or the one that I'm working on and we'll update and will appear here. So let's scroll down in that document to section 5, statistical methods. All right. We've already done a lot in this class, right? We've read a full data set in, we've worked on a code book, we have read in the data set, we've subsetted, we've renamed variables, we've coded our categorical variables, we've plotted univariate and bivariate relationships. And so now we are ready to start working on statistics. All right, so this section of week 5 from a previous year has both the regression components, which are these three, and then these next two, the logarithm scale, that's something we'll do next week. Okay, so I'm just going to click up here at class 5. Just as we did on our Tuesday, we had an intuition building exercise, and then this is basically where today's assignment will begin. All right, and by now the RStudio has finished compiling the document. I'm going to open the document that we are working on in the browser, and let's scroll down to class 10, statistical methods. In fact, let me just click on statistical methods and we'll walk through here a tiny bit. Okay, so class 9, notice it has a separate worksheet, so you've already done that in a separate document, and here we are in class 10. We have 3 objectives to complete. The first is to start with a bivariate scatter plot, and you can use the one that you made previously, or you can create a new one. And we're going to add a regression line. Okay, so you get 2 points right here just for adding one very simple line of code. That's pretty good. And then make sure you've labeled the axes and title. If you're using one that you had made previously, you get this point for free. So we'll look at this regression line. Then we're going to use the LM function, which stands for linear model, to fit a linear regression model, and we're going to interpret the slope and the R-squared value. We also interpret the intercept down here. So we're going to just fit the model and do a summary of the model. Get 2 points for that. You get 2 points for interpreting the slope. And then we're going to also interpret R-squared. Finally, we're going to also interpret the intercept from the regression model and determine whether it makes sense or not in the context of your study. Sometimes it doesn't. Though there are ways of changing the data in such a way that the intercept can make sense. There are these 3 subsections down here to put your results, and that's where we're going to work right now. So let's go over to RStudio, And we're gonna do a find. That's a control F, and I know it's like # space class 1 0. There we are. So I'm down at, for my file, I'm down around line 1300. For you, it could be something a bit different. All right, so let's go find a plot. So for me, okay, if I was you, in fact, should I pretend I'm you? Probably I should pretend I'm you. Give me 1 second to determine if that's what I want to do here. So I would scroll up to a bivariate numeric plot, this one right here, total cigarettes smoked per month versus age. Let me go see what I did in a previous year. Total cigarettes smoked versus age. Okay, that's the one. So yeah, I'm going to pretend I'm you. And so I'm going to, in RStudio, remember that I'm down around line 1300. Then I'm going to scroll up to my bivariate scatter plot. It was the first bivariate plot that we made. Here's the scatter plot. And it's the one, well, you know which one it is because both the x and y variables are numeric. Okay, so this is it. So I'm going to copy this code chunk, including the triple tick with the R. There we go. And now I'm going to scroll back down to line 1300 and put in my code chunk there. Hey. Well, something that I had you do last time. Oh yes, I added these 2 regression lines already. So this stat smooth method equals LM for linear model. That's what produces the regression line. All right, so let's take a look at this plot. I'm going to just work here in this space if I can make it all fit. Okay, so I've gotten a few questions about this recently. How do you get started running code when you come into it sort of without having run all the code from the top? So the first thing I always do is, regardless of whether my environment is empty or not, click the broom and say yes, and that's going to empty your environment. Then we need to set up your code, or excuse me, you need to set up all the objects in your environment as they would appear if you had knitted it, this knit, if you had knitted it from the top and run all the code. And you do that simply by hovering on this down arrow, run all chunks above, and clicking on there. It will open up the console, and oh, I made a mistake. Okay, I'm going to press escape a bunch of times and make it stop. And I forgot to set the working directory to the source file location. Okay, now it knows where to find the data file and everything else. Let's try it again. Hit the down arrow. It's good for me to make a mistake occasionally because for a few reasons, but one is that these are the types of things that you're likely to do, and I can show you the answer for those things. All right, I'm trying to make that plot window a little bit bigger. Oh, this happens sometimes. So this fatal error from R happened because you saw that I was resizing the plot window while it was running a bunch of stuff. That is problematic. You should not try to resize the plot window while it's trying to create plots and run other code. All right, so here we are again. We're down here. Let's see check our environment. Our environment's empty. So we can let's make sure that we are setting the working directory to the source file location and running it from the top here. Okay. These are actually really good things to have blow up as part of a video so that you can see what what's happened sometimes and not just think, why does it only happen to me? No, it happens to Erik too. Because Erik also gets impatient and wants to move things around. All right, it has finished. Because I'm going to be sort of doing new stuff down here, and we have got lots and lots of stuff in the console, I'm going to go down here and press Control L, which clears the console. I believe that might also be, it's up here somewhere. Let's see, does this do clear console? There we go, this little brush right here. I'm sure there's something up here that does it also, but I can't find it. All right, and let's also sweep clean all the plots. All right, so we have all the stuff in our environment that we need, but we've just cleared our working space down here. All right, let's just run this code to remind ourselves what this plot looks like. I know we don't want to do this geom smooth right here. That's the blue line, because we're just going to focus on this red line, which is the linear regression. So let me comment out the geom smooth. Okay, so I've commented out the geom smooth, and I'm going to reset the color just to be sort of the standard blue color that we get. And I think there's probably a few other things that we can do here. If I go back over to the previous year's example, I just use stat smooth method equals lm. This is good. This is just fine. All right, let's run it one more time, and we just have that one line to look at. And I'm going to click zoom when it finishes, which allows it to be a bit bigger. All right, we have people who are aged maybe 18 up to in their 90s. We have a blue regression line here, and it's slightly positively sloped. It goes up, so as age increases, the total number of cigarettes smoked per month tends to increase also. All right, so that interpretation is what we should see when we fit our linear regression model. So let's go back to our rubric and see what we say. Plot it with a regression line, label the axes and title. Axes and title look like they're there. Because I made a change to the colored line, I'm going to change the key here, just that the blue line is simple linear regression. There we go. All right, so I'm happy with the first part of the assignment. The second part is to fit the linear regression and interpret the slope and the r-squared values. Let's go grab some code for that, because that's what you would probably do. And this is all the code there is, really just 2 lines. I'm going to copy it with the comments, and then we will make the changes that we need to over here. Let's see, we can insert a code chunk. I pressed Control-Alt-I to insert, and I'm going to paste my code in here. All right, so there's a couple things here, and I'm going to reformat this a little bit just to help you see the different parts of what's here. Good, okay. So we've got, first of all, we need to tell the linear model function where the data is, and we're using the sarc sub. And then in the first argument, which is actually a sort of formula. Actually, let's look at the help for LM. Question mark LM down here. In the help window in the top right, it gives the arguments, and the first one is formula. Okay, so this is really formula equals the formula. And we've got the y variable, tilde, x variable. And it knows that we want to fit an intercept by default. If you didn't want an intercept, I think you can do 0 plus or something like that, or you do maybe you do -1 to remove the intercept. It's something like that. I do it so rarely that I always need to look it up if you need to do that for the formula. But anyway, so this is it, and then I'm going to assign the result of the linear model to an object. And my convention here is to say lm underscore, because it's a linear model object, and then I say what the y variable is, underscore what the x variable is. All right, so I'm going to highlight this and press Control Enter. That moved it down here. And if you type down here, if you look at that object, lm TCS, total cigarettes smoked, underscore age, and press Enter, it gives you sort of some disappointing output. It tells you how the regression model was fit, and then it just gives you the coefficients, the intercept and the slope. That's it. This is common for R. When you create an object, sometimes just looking at that object doesn't really give you very much information. But there are other ways to get information. In particular, summary. If I run that, now we get a lot of output. Okay. In the summary, we get the call again. This is the line of code that we ran that created the results. These residuals tell us something about whether our model assumptions are likely to be fit or likely to be met, and we're going to worry about model assumptions later in the semester. But typically we want our residuals, our vertical errors, to be normally distributed. If they were normally distributed with mean 0, then the median should be something close to 0. Right here we're not getting that. And the min in the first quartile being negative should be similar to the third quartile, and the maximum being positive. Here we have a lot of right skew for our residuals. Then we've got our coefficients table, and this is where we're going to be looking for this assignment. Under the estimate column, we have the intercept of our regression line and our slope for the regression line for when it's multiplied by age. These other columns we'll learn more about when we start doing hypothesis testing and so on, but they give you the standard error of the estimate, sort of your uncertainty associated with that estimate, a t-statistic, which is just the estimate divided by its standard error, and we use that t-statistic to calculate a p-value, which allows us to test whether this estimate is consistent with the null hypothesis that it equals 0, or whether it's different from 0. In this case, we have evidence that both of these are different from 0, and in some ways that means they're interesting. We have a line that just says something about significance codes. That's a key for the symbols that we see over here. We'll talk more about that when we talk about hypothesis testing. And then there's a bunch of stuff at the bottom. The only thing that we really care about is the multiple r squared. That's the r squared that we care about. Okay? And in this case, I get a 0.02. That's a very disappointingly low number. The rest of this, adjusted r squared and the rest, we use for model selection and for hypothesis testing. We'll talk about those things later on, maybe next semester. So the three numbers really that you need for this assignment are the intercept, the slope, and the r squared. Same numbers that we used for class 9. All right, So that was a lot of, as I've taught my young son, who's not yet 3 years old, that was a lot of blah, blah, blah. Just the adults going blah, blah, blah. All right, so let's make a little more space. Oh, whenever I adjust that, it makes everything shift. All right, and go back to the rubric and make sure that we're doing everything. And I'm just going to copy all this stuff down here and make sure that we answer each piece. All right, so we fit the linear model, this one right here, and we presented the table. That's this summary table right there. So that's done. Number 2, interpret the slope, and then the third one is interpret r squared. So I'll just say slope, colon, and then we'll do r squared. Okay, and probably the bolding won't work around the equation, but all right, so do you remember what the slope was? It was very low. Oops. Scroll up just a hair. There we go. Here is the slope. Oh yeah, this is maybe a good, well, I don't know, a good time when we could write a piece of code to put the actual slope in our sentence. In fact, let's do that. All right, this is a expert level stuff. So we've got this object, and we can look at what the names are of that object. Let me make some space. All right, I'm going to press enter. I pressed enter. There. All right, so there's like 13 things in here. The one that we are interested in, I believe, is the coefficients. So let's do this. We'll look at this $ coefficients. Yeah, that'll work, I think. All right. So there's the intercept and the slope. So if I do coefficients 1, it should give me the first one. And if I do bracket 2, that gives me the age. So I can refer to the slope with that piece of code. So I'm going to copy that. I'm going to bring it over here and left tick R space, paste that piece of code, left tick again. All right. So I'm going to let me interpret the slope, and then I'll come back and we'll put this code in there to do what we want. Oh, one more thing is that number is good, but it's going to be too long. So let's make this significant digits 3. So we'll restrict it to 3 significant digits. All right. So we got the slope. So we'll say the slope is 3.79. And quite honestly, I don't care very much about whether you do your rounding correctly very much, but let's do the rounding. The slope is 2.8. Therefore, so I say the slope is interpreted with respect to a per unit increase of x of the x variable, meaning that, therefore, for every, let me write it very generally and then I'll plug in the exact interpretation. Therefore, for every unit increase in x, we expect an increase of 2.80 for y. That's it. All right, so now I'm just going to plug in the actual thing for me. Therefore, for every year increase in age is the x variable, we expect an increase of 2.80 total cigarettes smoked. That's it. All right. So the last thing is, can we use this piece of code to plug in to fill in the 2.8? Okay. We actually don't need this first piece where it says the slope is 2.8. I'm just going to say for every year increase in age, we can say for every 1 year increase in age, that's good, we expect an increase of, I'm going to put this here, and we'll see. You can put line returns, by the way, and as long as you don't put a blank line in between, it will put them all together in one sentence. Okay, I think that's a little easier to read. All right, let's knit this and just check this part, and then we'll come back and we'll interpret R squared. All right, so knitting. It actually looks like we can work on it while it knits. All right, so I'm happy with the interpretation of slope. Let's go to R squared. For R squared, this is the proportion of variance explained by the regression model over and above, or compared to the grand mean is, and then we just put in the R squared value right here. I don't remember what it is. It was like something disappointingly small. Okay, so we'll come back and we'll fix this number right here. All right, so we got the result. This is what we're working on. I'll refresh that. And class 10. Okay, sorry I'm jumping all around. Here we are. Class 10, this is what we're working on. We've got our plot with our regression line. That looks fine. We've got our regression model that we fit here. We have the summary. We've got the slope. For every 1 year increase in age, we expect an increase of 2.8 total cigarettes smoked. So that 2.8 is coming from the code right here, an increase of 2.8. Maybe a significant number of significant digits of 3 is too small. It even dropped the 0. So I just make that 4 significant digits. Okay, that's pretty good. The last thing is to interpret the R squared. Here is the R squared. Let's do the same thing with R squared. We'll grab the value. All right. From the linear model object. So look at the names, and now we've got to find the R squared. And this always takes me a little bit of time. And a lot of these things are not really named the way you would expect them. Like terms, I think, is something weird. Yeah. All right, names. I think effects is something weird too. Yeah. Oh, I know what it is. So we've got this summary. I'm just pressing the up arrow a bunch of times. So this summary, this is what happens. This produces all this output. And in particular, there's a few objects in this summary. Let's look at the names of the summary. That's where it is. So when you do summary, it produces all this other stuff. In particular, R squared is right here. There's also the table, the coefficients. Okay, so if you wanted to refer to, so here's summary, $ coefficients, that gives you this coefficients table here. Okay, and then you could grab like a t-statistic or a p-value out of there. And I think like this p-value would be the second row, 1, 2, 3, fourth column. Let's see if we can get it. Second row, fourth column. Nice. Okay, that's how you grab that. In our case, we want the $$ squared, and that is this number right here. Perfect. So this is the object that we want to put in our report. R squared equals, so instead of typing that number, I'm going to put tick R space paste tick, and I'm also going to make it 3 significant digits. The last thing I'll say is that this R squared number, which is very small. Okay, I would consider that part of the interpretation. All right, we can knit that, and I think we're going to be happy with that part of the assignment. Let's move on to the next thing, which was interpreting the intercept. Okay, and does it make sense? So we'll scroll down here. Looks like the heading is the same as the question basically. Okay, so does the intercept make sense? If we look over here at the console, our intercept is 57.9. Oh, you know what? There's one more comment I want to make, and I've just moved this while I'm knitting. I think that's probably going to be okay. I think this total cigarettes is per month. So I want to add that to my interpretation. I'm sorry, I'm jumping around a little bit. We expect an increase of that many total cigarettes smoked per month. Okay, that's all. All right, let's go back to our intercept. So we've got, say it's about 60, okay? So we've got about 60 cigarettes per month. That's what I wanted to see over here. The y-axis says per month. Okay. All right, our intercept is 60. What does it mean? Let's zoom in on our plot for a moment. What is the intercept? It is, in fact, our plot doesn't even go far enough to see our intercept. It's the value of y, of the y-axis, when x, age, when x equals 0. So if we take this blue line and we continue to extend it to the left, it will eventually age will equal 0. In fact, let's just add something to this plot so I can show you in this particular plot what that looks like. I believe I can do xlim equals C0 NA. That basically says I'm setting a lower limit of x equal to 0, and I'm not defining the upper limit. Oh, and then the other thing is there's like a stat smooth. You can see over here that the regression line stopped at where the data stopped, and there's a way to like do full width where it doesn't stop at the full range. I want to make this true. Full range means that the regression line will continue beyond the scope of the data. All right, let's rerun this piece of code here. It's not going to fit in this window, but then I'll zoom and we'll look at it. I clicked, it flashed, and then, okay, there we go. So here's the regression line going all the way back to 0. So my question is, interpret the intercept, and does it make sense? Okay, so what does it mean? The intercept is when age equals 0, the expected number of total cigarettes smoked per month are. So we can interpret it. Let's just type that interpretation right now. Okay, the expected number of cigarettes smoked per month is, I'll come back and fill in the value, is 60 for someone aged 0. Okay, you know what, I sort of like putting this first. For someone 0 years old, the expected number of cigarettes smoked per month is whatever it was. Let's grab that table. All right, 57.9. Does it make sense? This does not make sense, since newborns do not smoke. Okay. Often, the intercept is far beyond the scope of the data, so it's not going to make sense because it's an extrapolation from the data, or it's not going to make sense because it's just impossible. There's lots of reasons. I could also say, since newborns do not smoke, and because this is a large extrapolation from the data. Okay. That is the full assignment. Let's knit this and oh, you know what? I used the code for the slope. I might as well put the code for the intercept in here. I'm just going to copy all that stuff, come down here, and paste it in here. And recall that the coefficients 1 was the intercept and 2 was the slope. So I'm going to change this index to 1 for the intercept. And we'll review the results, and that will end the video. This was a fairly short assignment, especially given what we did for Tuesday's assignment, class 9. All right, these poor geom smooths making my CPU run like crazy. All right, let's refresh here. Okay, looks like it's stopped jumping around. We've got full range in here. This is not really necessary. You don't really need to put in an X limit, but if you do, you can, of course, and then it sort of helps you see what that intercept looks like when it's superimposed on your data, especially if it's an extrapolation like mine is. All right, so we fit the linear regression model. We've got our interpretation of slope. For every 1 year increase in age, we expect an increase of 2.8 total cigarettes smoked per month. R squared, the proportion of variance explained by the regression model, is 0.02, which is very small. Interpret the intercept. Does it make sense for someone 0 years old? That's the value of x, or it's the x variable at 0. The expected number of cigarettes smoked per month is 57.9. That's the number that I typed in manually. I've not re-knitted this since then, but I will now. This does not make sense since newborns do not smoke, and because this is a large extrapolation from the data. That's pretty good. Go back to the rubric just to double check, and I think we've got everything. So that is the end of this video. I'm going to wait and make sure that the one change that we made here comes in just fine. And then I'll make one more comment. I added something to the outline file since last time, and I just want to mention that it's there in case you have some dates that you would like to work with. This poor window keeps moving every time. Alright, wrapping up. Let's come back over here. We'll refresh the page, and the only thing that we're looking for that could change is the value of the intercept. That's the one thing that I wrote code for. So I'm going to press F5. You can also do Control R or something. And here's the intercept. Okay, so that's the computed value. Looks pretty good. All right, the last thing I want to mention, I'm going to jump up to the top. Under data management, I've got a section on working with dates. I'm going to click on here to jump down. And I say this is how to calculate the duration between two dates, and that you probably won't need to use this for your project. But what would be an example? Say you've got, well, I don't know, the only example I could really think of is we've got an interview date and we've got a date of birth. And the interview date starts with these C variables, and which are these three right here, and then the date of birth is there. And there's also an age variable in the data set, which is the age of the person when they took the interview. And so what I do here just very briefly is I just create a data subset just for this example. I select these variables and I create a date out of the C date, C month, and C year. In fact, I see I've sort of put in some extra stuff here. In a version that you'll see that's not in this video, I'll delete these leading dat_sub. Anyway, so I paste together the day, the month, and the year, and then I use a function from the package lubridate, which looks at the text that we just made and it interprets the numbers that are in there as a day, a month, and a year, and creates a date object. Okay, I then also do the same thing with the date of birth, day, month, and year. Put that into a date of birth text. I interpret the date of birth text using the date, month, year function. So I've got a date there. And when we look at some of those objects, these are the original variables. We have the person's age, say this 23-year-old. They were born, or they were interviewed on the 14th of August 2001, and their birth date was in 1977, September 27th. Then I created a C date text, which were just taking these three numbers and putting them together in one string. That's what's here, 14, 8, and 2001. We have the same thing, but for, and then that text I interpreted as a date. And when it read it as a date, here's what it gets. It goes into a date format, which is year hyphen month hyphen day. And then I do the same thing for the date of birth. So here's someone's date of birth, which came from here. Okay, so there's the date of birth, there's the text there, and when it was interpreted, there's the date object. Once you've got the date objects, then you can start calculating differences. Like, here's the difference between the interview date and the date of birth. and that gives you the age, a person's age when they were interviewed, in the number in days. Okay, so that difference is calculated in days. If you divide it by 365, you can get their age in years. And this age difference is just to calculate the difference between the fractional age and the integer age that they gave. So here are these three new variables. This person was 8,722 days old when they did their interview. That is 23.8 years old. And the age difference between what we calculated and what they gave for the interview is just this fractional part here, 0.8. And that's it. That's basically it of that section. Okay, that was longer than I expected, but I hope you learned a lot through some of the computer crashes and some of the details about how to use this coding here to input automatic values into sentences. I use this all the time in my own work. All right. See you on the next one.